Complex numbers. Basically what complex numbers are real and imaginary numbers. First of all, understand this. I is the imaginary unit. What I is the square root of -1. If you ever see square root of -1, it is equal to I. Square root of -1 is not a real number. It does not exist in the real number system because in the real numbers, you can't take square root of negative numbers because you can't square a number and come up with a -1. So if you had to solve this equation, you ask yourself, well, x squared equals -1, and what number could that be? Well, it's not a real number. No real solutions to this equation. However, if you did square root it, you get imaginary solutions. Square root of x is x, and square root of -1 is I. In this case, we're going to call it positive or negative I because we did square root and solve for a variable. But basically what that means is square root of -1 is I. So understand this also. I squared equals a -1. If you ever square I, you want to get a -1. So that's what it is. What a complex number is a real number plus an imaginary number. So complex numbers encompass all imaginary numbers. Complex numbers. It's going to be a real number like 7 plus an imaginary number like 3i. That's considered a complex number. Why? Because you got a real part and an imaginary part being added together. Technically, any number can be considered a complex number. Because if I gave you number 3, I can easily make that a complex number. How? I can just add 0i to the end. And now it's a complex number. So basically, any number you actually have can be considered a complex number. There's another set of numbers called pure imaginary. Pure imaginary numbers are numbers with no with no real parts to it. So if I gave you like 3i, that's a purely imaginary number because you have no complex number added to it. However, I can also make that a real number as well, a complex number as well. If I took 3i, if I added 0 to the end, I haven't changed the number, and now it's complex. Purely imaginary doesn't actually show you the addition of a real number to it. However, any purely imaginary number could also be easily converted to be complex simply by adding 0 to it, making it real plus imaginary. So why is that useful? Well, it's very useful when we're dealing with numbers that you take square root of negatives. And we do see that in math. Even though they're not real numbers, we see them, and we have to have a way of dealing with them. All right, so the directions say simplify each one of these expressions. None of these are real numbers because you notice each one has a square root of a negative number. So automatically I know it's imaginary. The way we actually simplify it is the square root of -4 is really the square root of -1 times +4. Why? Because -1 times +4 is -4. So if that's the case, I can square root the first term, square root of -1, times square root of the second term, square root of 4. We already know this square root of -1 is I, square root of 4 is 2. So we have is I times 2, or 2i. Basically what I've learned is whenever you see a negative sign, you automatically just bring an I outward, making that I square root of 4, which you now know I times 2 is 2i. But the reason why it works is -1 times that number. So if I saw this one, square root of -11, I would simply call it I square root of +11. Now you can't square root of 11, so that's what it is. So this is simply I square root of 11. In this case, I also have an imaginary number, so it's I square root of 2 all over 6. And this can't be simplified any further. All right. So anyway, that's how you simplify them, that's how you work with them, just with the imaginary part. Let's talk about them some more. All right, so adding complex numbers work pretty much like you think you would. That 3i and 4i and so forth, 4 plus I, pretty much act like variables. So we have no sign in front of the parentheses here. There's understood 1 right there. So if we multiply 1 to each of those, they don't change, making it 4 plus I. There's a plus sign here with the understood 1 in front of this set of parentheses. So 1 times each one doesn't change either of those, making it plus 6 plus 3i. Now you look for your like terms. You have an I and another I, 6 and a 4, making it 10 plus 4i. So we find an answer for that one. In this next one, we have an understood 1 in front. That doesn't change anything in that set of parentheses, making it 5 subtract 3i. This has subtraction. That's an understood 1 as well. So negative 1 distributed into the parentheses changes both of their signs, making it a negative 2 and a positive 2i. Then our like terms are 3i and 2i. Give you 5i. Negative 2 and a positive 5 leaves you with 3. Positive 3. So that's the answer for that one. And look at this last one. You want to look for what actually, well, we have a negative sign here. This is understood negative 1. That changes both of their signs. This positive sign here, so it's positive 1. That does not change any signs. And this 4 just carries over, making it 4. This is a negative 3i, subtract 9. Negative 3i, subtract 9. And then 4 plus 5i. Combining my like terms, I have an I here, an I there, add to be an 8i. Positive 4, subtract 9 is negative 5. Add 4 to it, gives you a negative 1. And that would be the final answer for it here. All right, so anyway, that's how you add them. Pretty much work pretty intuitively. I'll get that down as a note. I'm about to erase the screen. All right, so multiplying complex numbers. They work a lot like you think they do as well. For example, 5i distributed into this parentheses would make it negative 10i plus 5i squared, because I times I will give you I squared. Now what we know is I squared has a value. It's a real number. It's negative 1. Means that this is negative 10i plus 5 times negative 1, which is equal to negative 10i subtract 5. So our final answer for that is negative 10i subtract 5, because the I squared is really substituted to be negative 1. Going on, look at the next example. And these, we want to fold those together. And when we do, you distribute 7 to each one, making it a 7, negative 7, and then plus 14i. And then distribute the negative 4i to both, making it a positive 4i. And a subtract 8i squared. These are like terms, so they can combine. That has an exponent, that's really negative 1. So it gives you negative 7 plus 18i, because these have to be 18. Subtract 8 times negative 1. So it makes it negative 8 times a negative 1. Meaning this is negative 7 plus 18i plus 8. So these are now like terms. Negative 7 and 8. They have to be a positive 1. So 1 plus 18i is what you get after you fold those two together. And the last one, I'm going to pause it. I want you to pause it. Actually try that one on your own. Actually fold together 6 plus 3i and 6 subtract 3i. And after you finish pausing, see if you get the same thing I have. So after distributing them both together, I got 36 subtract 18i plus 18i subtract 9i squared. These are like terms, and they have the exact same values but opposite signs. So because of that, they count out to be 0. Give you 36 subtract 9i squared, which is nice because I know I squared is negative 1. Makes it 36 subtract 9 times the negative 1. Makes it 36 plus 9, which is 45. So the product of these two gives you a whole number. It's a real number, which is 45. Just so you know, these two are called conjugates. 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 Basically what they are look like a difference of two squares if you think about their factors. One has a plus 3i and one has subtract 3i. Other than that, everything else is the same. Those are called complex conjugates, and basically when you fold them together, you should get a whole number because all the imaginary parts will cancel out. All right, moving on. And before I move on, I had to correct that a little bit. Made it look a little better. That A didn't look much like an A at first. All right, so complex conjugates, let's actually use them and talk about why they're useful. If actually to simplify this expression, the only problem with it is you have an imaginary number on the bottom. We learned other classes we don't like square roots on the bottom, and now we also don't like radicals. We don't like radicals on the bottom and square roots on the bottom. We also don't like i's and imaginary parts on the bottom. So if we see that in math, we generally don't like it, and we want to change it so that it's not like that. So in that case, if that's the case, I actually want to rationalize this denominator, so I don't have a imaginary unit there. So that means I want to get rid of this I. How I can do that is multiply this by its conjugate. And the conjugate of 4 subtract 5i is 4 plus 5i. I'm going to multiply by that over itself. Why again? Because 4 plus 5i divided by 4 plus 5i is 1. Making that a unit multiplier. Meaning I'm multiplying it by 1 and only giving it a cosmetic change, not a real change. So when I do that, my numerator is now 3 plus 2i times 4 plus 5i. That's going to be divided by 4 subtract 5i over 4 plus 5i. You're going to fold those together, and I kind of know what the bottom's going to wind up being. After you fold that together, you should wind up having 16 plus 25. In the numerator, it should wind up being 12 plus 15i plus 8i plus 4i squared, which now equals to, on the bottom, 16 and 25 should give you 41. In the numerator, what we should have is 12 plus 23i, subtract 4. Why subtract 4? 4 times a negative 1. It's negative 4, so subtract 4. So the numerator is now 12 and negative 4 are like terms, giving you 8 plus 23i all over 41. And this is the simplified form of this expression that we began with. Why is it simplified? We no longer have an I in our denominator, and that's what we don't want. And now we can actually have it where we don't have an I in the bottom by using the conjugate and multiplying the numerator and denominator. I'll get that as a note as well. I'm going to move on. All right, last topic dealing with complex numbers is this, actually graphing it. So if I actually want to graph the complex number, I need a complex axis. This is a complex coordinate plane, actually. So this is a complex axis. But as a complex coordinate plane, the reason why is we have a real axis, which are real numbers. We have imaginary axis, which are your imaginary numbers. So all these are imaginary numbers, 1i, 2i, 3i, 4i, 5i, and so forth. So if I want to graph the complex number, graph 3 plus 5i, you're going to graph the real part and the imaginary part. So the real part first, imaginary part next. So I will go over 3 on the real axis, up 5i on the imaginary axis. So this is the point, 3 plus 5i. And that's how you graph it. Suppose I gave you a new graph, such as this one, graph negative 2 subtract 4i. We can go over to negative 2, you can go down to negative 4i. This will be the point, negative 2 subtract 4i. If I was actually to graph something like just 6i, the real part is 0. So you can go over 0, up to 6i. So that would be the point, 6i. That's be a purely imaginary number. All right, so anyway, that's it. We got some other things to talk about, like finding the absolute value of this. Like we want to find the absolute value of 3 plus 5i. That's essentially actually how far that is from the center or whatever. So actually from the origin. So basically what you do is you square the first term, square the second term. Well, square the coefficient of the second term. Square 5, you get 25. Giving you the square root of 34. So this link here has to be the square root of 34. So that's how you can find the absolute value of it. Anyway, that's all I have. Good luck.